The topic of today's video will be Cauchy's residue theorem, and in this video we will see the application of residue, right? The a minus 1 coefficient of the principal part of a function, right, which has a singularity at z equal to z naught. As we discussed in the last video, we learned how to find the residue of a complex valued function, right? So we will evaluate the contour integral in this video with the help of that residue, right? So I will start to state this Cauchy's residue theorem. The statement: let D be a simply connected domain and capital C is a simple closed curve inside it, right? If f z is analytic within, what should I write, on and inside C, with finite number of singularities at z1, z2, dash zk, then line integral of fz dz around closed curve C is equal to 2 pi eta times summation residues evaluated at zk, where k starts from 1 to, should I write it as r or n? N starts from 1 to k. So this is the statement of Cauchy's residue theorem. It says that you have a simply connected domain D. By simply connected, we mean that a domain D without any holes inside it, right? And that's why we are calling it simply connected. So what do you need? You need a simply connected domain D and a simple closed curve lying inside that domain D, right? And you assume that your function fz is analytic within C or inside C and as well as on its boundary, right? And it has finite number of singularities at these points z1, z2, zk, and all of these points lying within C, right? I should write it here, lying within C. Singularities is inside C. Inside C. Then by Cauchy's residue theorem, the line integral of fz along that closed curve C is equal to 2 pi eta times the summation of residues, and all of those residues are evaluated at these singularities, right? Okay. So I will draw a small figure for this. However, that is not actually needed. So this is the domain D of any arbitrary shape, right? Domain D, right? And inside your domain D you have a simple closed curve C, right, like this one, and conventionally its direction is taken as anti-clockwise, right? Okay. And there are singularities inside this curve. Suppose this is your z1, this is z2, and so on, and you have zk here, right? So there are k singularities inside this curve C. Then theorem says that evaluation of your function along this closed curve is actually equal to 2 pi eta times the sum of all residues evaluated at these singularities, right? And you know it well how to evaluate the residue, right? Okay. So this is a statement of the theorem, and it directly implies from Cauchy integral formula. I will give a short proof for it, right? We'll use Cauchy integral formula for its proof, right? Okay. So I will write the Cauchy integral formula again, and that was, we know that the Cauchy integral formula was something like this: gz over, I am writing gz here, however we have written fz there, right? Gz over z minus z naught to the power n plus 1 dz, or should I write it n only, equal to 2 pi eta, and in this numerator function we have g n minus 1th derivative evaluated at z naught, and I think here we had n minus 1 factorial also, right? So this was Cauchy's integral formula for derivatives, right? The second version of Cauchy's formula. We had two formula actually: the Cauchy's first integral formula and the Cauchy's second integral formula that involves derivative, right? Okay. So this was your Cauchy's integral formula and second formula, right? So what I will do, I need this, I need fz, but here we have this one, so I will replace this by fz, right? Okay. Or it can be written as integral c g z over z minus z naught n dz equal to 2 pi eta over n minus 1 factorial, and if you see this is actually the n minus 1th derivative of gz evaluated at z equal to z naught. So I will write that in this way: d n minus 1 dz n minus 1 of gz evaluated at z equal to z naught, right? And in order to achieve this result, I will replace this quotient function by fz, right? Okay, right? Gz over z minus z naught to the power n equal to fz, right? In that case, my last equation will be converted into integral, line integral along c fz dz, right? And you see that we have this integral on the left hand side equal to 2 pi eta, right? And this 1 over n minus 1 factorial, and here we have d n minus 1 dz n minus 1, and gz will be, the value of gz will be z minus z naught to the power n multiplied by fz, right? And that value is evaluated at z equal to z naught, right? So I will write that here, z equal to z naught, right? And eventually this is the formula for residue, right? For a pole of order n, if you remember the formula from our last video, right? So I will replace this by 2 pi eta into multiplied by residue evaluated at, residue of fz evaluated at z equal to z naught, right? So in general, this is for just one singularity. If we have k singularities as we have here, then at each singularity we'll calculate residue, right? And then we'll sum all of those residues and then multiply it by 2 pi eta, right? And why we are summing all of those residues, the important point is that because as you know from the Cauchy's theorem, for multiply connected region we just replace the outer curve by simple circles, and all of those circles must enclose one and only one singularity. If you remember that working of Cauchy's theorem for multiply connected domain, the outside curve, this curve is replaced by simple circles, right? And the first circle is C1, the second circle is C2, the kth circle will be CK, right? And remember that all of these small circles must have radius as small as possible in order that they should not overlap with each other, right? I will write that point here, right? In general, for singularities Z1, Z2 up to Zk inside C, using we call that Cauchy's theorem for multiply connected region, that is replacement principle, right? We replace the outer original curve by small circles, right? And those circles have been drawn here in the picture, right? We get this result. Integral C fz dz is actually equal to the integration along these small circles, right? And then we add them all, right? So 2 pi eta, and here we will have summation this time because all of those residues will be added up, right? Due to this replacement principle, summation residue of fz evaluated at z equal to z naught, or should I write it z equal to zn, and n starts from 1 to k, right? So this is a small proof for this Cauchy's residue theorem, right? And one more thing, in all of these theorems, on statement of these theorems, we assume that the orientation of C is anti-clockwise. The first thing is that that's why we place plus sign here, right? If the orientation is taken clockwise, then we'll put negative sign here, right? The first point is that. Second point is that in all of these statements of these theorems, we assume that the winding number of the curve is 1, right? By winding number, I mean the number of times the curve winds the singularity is called the winding number, right? In that case, for general, if you have winding number equal to n or omega, then you will put omega here, right? I will write that statement here for winding number. If winding number of curve C is omega, I am writing that omega, then this result becomes fz dz equal to 2 pi eta multiplied by winding number, right? And then summation n equal to 1 to k residue fz z equal to z naught, right? So this is the most general result where we have multiplied this right hand side by omega. Omega is called the winding number, the number of times this curve encloses the singularities, right? Okay. Suppose you take e to the power eta theta, z equal to e to the power eta theta, it means that a circle, right? But if you write z equal to e to the power eta 2 theta, then it will be a circle traced twice because the angle is doubled. If you write e to the power eta k theta, again it is a circle centered at origin and radius equal to 1 obviously, but the circle has winding number equal to k. It means that circle is traced k times, right? Okay. So I will take examples of this Cauchy's residue theorem. First example. Example number 1. Evaluate integral e to the power z dz over z square 2z plus 1, and C is where C is minus 1 by 2. That should be mod z. If I take a circle that encloses both of these singularities, that should be mod z equal to 2, right? Okay. Solution. Okay. In order to use this theorem, I will just search for the singularities inside the circle. See my circle is mod z equal to 2, and the singularities of this function are at 0, and here from here I will obtain minus 1 by 2, right? So singularities are, or should I write their poles obviously, clearly. Z equal to 0 is a pole of order 2, and why I am writing that it is a pole of order 2, because z equal to 0 will be obtained twice, means that multiplicity is 2 and the order will be also 2, because the numerator is analytic at that point, right? So be careful at that point. And z equal to minus 1 by 2 is a simple pole, right? So I will draw a small picture for this, right? Mod z equal to 2 is a circle, this complete circle. This is mod z equal to 2, and your singularities are at 0. This is a singularity 0, right? And another singularity is at minus half, right? And you can see that both of these singularities are within your circle C, right? And one more thing, it is not necessary that the C is always of the form of circle. It can be a triangle, rectangle, square, anything, a closed figure, closed polygon, right? The theorem works well in all cases, right, irrespective of the shape of this C, right? Okay, so I will find residue at z equal to 0 first. That should be equal to, since it is a pole of order 2, I will use the formula 1 over n minus 1 factorial, I think that is 2 minus 1 factorial, and d by dz of z square times fz, right? And then it is evaluated at z equal to 0, right? We have used this formula that we derived in our last video, right? It will become 1, and z square multiplied by fz will cancel this z square. Ultimately I have to differentiate this e to the power z upon 2z plus 1, right? Okay, and differentiating this e to the power z over 2z plus 1 once, I will get 2z plus 1 whole square, 2z plus 1 multiplied by e to the power z minus e to the power z multiplied by 2, and then this value is evaluated at 0, right? So plugging z equal to 0 here, I will get this will become e to the power 0 1 minus 2 minus 1, and yeah, minus 1. So minus 1 is the answer, residue for z equal to 0. Now evaluating residue at the another pole, and that is minus half. So since it is a simple pole, I will use the first formula, that is equal to limit z tends to that pole, and z plus 1 by 2, since we have z minus z naught here, so in place of z minus z naught I am having z plus half, right? Okay, multiplied by your fz, and that will produce limit z tends to minus 1 by 2, this multiplied by fz will give me e to the power z, and you should take this 2 common, you will have 2z square. Okay, fine. So on cancellation you will get this. Be careful at this point, because you should have to take this 2 common, right, in order to get this z plus half cancelled with this, right? And then you plug your minus half here, you will get e to the power minus half, and it will become 1 by 4, right? So ultimately 2 will appear in the numerator. Fine. Therefore, using Cauchy's residue theorem, now I have 2 residues, I will sum them and then multiply it by 2 pi eta, right? And since the orientation is also taken as anti-clockwise, however it is not stated, but whenever it is not stated, you should take the orientation in anti-clockwise direction. That is conventional, right? And the winding number is also taken as 1 unless and until it is stated in question, right? Okay, therefore integral of this thing c e to the power z dz over z square 2z plus 1 equal to 2 pi iota multiplied by sum of residues, and residues are minus 1 plus this thing minus 1 plus 2 over square root of e. So this is the answer, right? Taking another example. Example number 2. Evaluate, let me call it I, dz over z square plus 4z plus 13, and here c is mod of z minus 3 iota equal to 3, right? Solution. In order to find its singularities, we will just equate the denominator equal to 0, right? The singularities are given by, right? Putting this denominator equal to 0, and then on factorization I will have z equal to minus 4 plus minus 16 minus 52, that will be 36 minus 36 over 2, and I think that will give me minus 2 plus minus 3 iota. Yes, so I have two singularities and both of them are poles. Why I am calling them poles? Because I know that if I differentiate this denominator, I will get 2z plus 4, and at these points that will not go to 0 definitely, right? So they both of them are poles, are simple poles. They are simple poles, right? Okay, and we have to check that whether both of them are lying inside C or one of them, right? So I will draw this circle first. My circle is centered at 3 iota, so 3 iota will be here, something here on y-axis, right? 3 iota is, this point is 3 iota, and the radius is also equal to 3, so it will be something like this, touching this x-axis, right? X-axis, and this is the y-axis. This point is 0, this point is 6 iota, right? And now you look at your poles. This is minus 2 plus 3 iota, and it is very difficult to identify that where will it lie. Minus 2 plus 3 iota, minus 2 plus 3 iota, minus 2, whether it will lie outside or inside, it is not easy to detect from the picture, right? The easiest way is that you should just plug these values here in the circle, right? Okay, so what I will do, I will plug these poles, minus 2 plus 3 iota and then minus 2 minus 3 iota, one by one in my circle equation, right? And I will identify that whether they lie inside or outside this circle, right? So this is a C. Okay, now I will check. This is your checkpoint. Z1, for Z1 is your minus 2 plus 3 iota, right? And just plug this value here, minus 2 plus 3 iota minus 3 iota, right? And I think that will give me mod of minus 2, and that will be ultimately equal to 2, right? And see this 2, obviously this is the distance between this number, complex number, this pole and the center is less than 3. You can see that the radius is equal to 3, but the distance between the first pole and the center of the circle is 2, right? It clearly indicates that this pole lies inside this circle because the radius of the circle is greater than this distance, right? Which is less than 3. Therefore, Z1 lies inside C, right? Now for the second one also, Also, mod of the second pole is -2 -3 iota, and then -3 iota from the circle. You will get -2 -6 iota, I think, right? Okay, obviously that will lie outside because it will lie in third quadrant. Both of the x and y ordinates are negative, right? It will lie here, right? So ultimately it will become 4 plus 36 and square root of 40, and that is obviously greater than 3. So you can see that this is outside, right? Okay. Now outside C, right? Now I will find the residue of Fz at z equal to the pole lying inside, that is -2 plus 3 iota, equal to, since it is a simple pole, so I will use the first formula, limit z tends to -2 plus 3 iota, and z plus 2 minus 3 iota multiplied by Fz. You just pay attention to this point. Z tends to Z naught, means Z minus Z naught, right? And you see your Fz is of this form, right? So limit Z tends to -2 plus 3 iota, and here we have Z plus 2 minus 3 iota, and your Fz is of this form, 1 over Z square plus 4Z plus 13, but that is factorized, right, in terms of its roots. The roots are -2 plus 3 iota and -2 minus 3 iota. So whenever you have a quadratic equation, x square plus ax plus b type, right, and you have roots alpha and beta, so you can always replace that equation x square plus ax plus b by x minus alpha into x minus beta, right? Means replacing that quadratic polynomial in terms of root of its factors, right? And those factors should be z minus first root, that is z plus 2 minus 3 iota, and z minus second root, and second root is -2 plus minus 3 iota, that will be +2 plus 3 iota, right? And in this way this will be cancelled, and then you will plug your z here, and if you plug your z here, then -2 will be cancelled, 1 over 6 iota, I think, 1 over 6 iota, right? And you should rationalize this with iota, you will get minus iota by 6, and the rest is to use that Cauchy's theorem, 2 pi iota multiplied by this thing, right? I should write that here only. Therefore, using Cauchy's theorem, the answer will be 2 pi iota multiplied by minus iota by 6, and it will become pi by 3, right? Okay, so in this numerical you have seen that in order to check whether a pole lies inside or outside C, you should just rely on this basic fact. The distance between two complex numbers z1 and z2 is given by mod of z1 minus z2, right? Okay, taking next example. Example number 3, evaluate I equal to tan z over z dz, and the circle is mod z minus 1 equal to 2, right? You can see that the circle is centered at 1 and the radius is equal to 2, right? Okay. Solution. So first you see your function, it is a quotient function tan z over z, and you should write it as sin z over z cos z, right? Okay, fz equal to sin z over z cos z, and the circle is this, centered at 1 and radius equal to how much? 2. It means that it will pass through from here, right? Something like this. X-axis and y-axis. This is z equal to 1. It should be z equal to 3, and it should be z equal to -1, right? And now I will find the singularities, right? If you put denominator equal to 0, right, just put this denominator equal to 0, you will get z equal to 0 from this, and cos z equal to 0, and cos z is 0 at odd multiples of pi by 2, 2n plus 1 pi by 2, right? So I am writing those singularities directly. Singularities are, and obviously they will be poles, right? The type will be pole, right? So poles are z equal to 0, that is obtained from here, and z equal to 2n plus 1 pi by 2, where n is an integer, right? Okay. And all of these poles are simple poles, right? And why I'm calling them simple, because if you differentiate your denominator, just the denominator, you will get the first derivative, which is non-zero at each of these points, I think, right? If you put 0, differentiation will be z sine minus z sine z plus cos z. Yeah, it is non-zero. Okay. So residue of fz at z equal to this one, but out of these so many poles, only I think pi by 2 and minus pi by 2 will lie inside it. Yes, I should write that first. And from here, only z equal to 0 and z equal to plus minus pi by 2, I think it is 3 pi by 2, 1.5. And if I write 3 pi by 2, that will be outside. Yeah, only plus minus pi by 2 will lie inside C. Lie inside C, because the value of pi is 3.14, and if you divide that by 2, you will get 1 point something within your circle, right? And the other values are 3 pi by 2, that will lie outside the circle, right? First, I will evaluate the residue at this point only, because this is at this point that equal to 0. The numerator is also going to 0, right? So I have to rely on some other thing, maybe on the Laurent's expansion, in order to evaluate residue at this point, right? Because all of my formulae will fail at this point. Okay. Yes. So therefore, first finding residue at pi by 2, right? So if I find residue at pi by 2, I can use that simple pole formula, that is numerator as it is, and differentiation of denominator, that will minus sin z plus cos z, and then I will put z equal to pi by 2, and on plugging pi by 2, I will get 1 in the numerator, and I think this will be minus 1. So ultimately the answer will be minus 1. And residue of fz at z equal to minus pi by 2 equal to, again using the same formula, sin z over minus z sin z plus cos z, evaluated at z equal to minus pi by 2. I think this time in the numerator I will be having minus 1, and in the denominator I will be having, this will become, I think I missed something, that should be z equal to pi by 2, and sin 90 is 1, minus 1, and this is pi by 2, so 2 by pi, minus 2 by pi. Okay. So minus 1, and here I will have, this will become plus, right? So ultimately it will become 2 by pi again, right? Minus 2 by pi, minus 1, and it will become minus pi by 2, and then it will become plus sine minus 1, right? So it will become 2 by pi, I think, if I am not wrong. Yes, it will be 2 by pi, right? And now evaluating residue at z equal to 0, right? To evaluate residue fz z equal to 0, you should rely on the original principle to find the residue, right? And that is the Laurent's expansion, right? Expand fz around z equal to 0, right? And now expanding fz equal to tan z over z. This is 1 over z, and I have to use expansion. And one more thing is that if I plug tan z over z is this, if I plug z equal to 0, I will get tan 0 by 0, right? A shortcut way. And if I then I use that L'Hospital's rule, I will get sec square z over 1, and sec square 0 is 1. So it indicates that z equal to 0 is a removable singularity, right? And that should be corrected here. I think singularities are right. Singularities. It is not a pole actually. Z equal to 0 is not a pole. It is a removable singularity. And you know that if a point is a removable singularity of a function, then that function can be converted into an analytic function by supplying a proper definition of function at that point, right? And if it is an analytic function, then you cannot get negative powers of z, or you can say that the coefficient of 1 by z will be 0, right? So use that logic rather than expanding tan z and getting the same answer. I should write it directly. The residue should be equal to 0, right? Or you should check it by yourself on expansion, right? Okay, expand this around z equal to 0, and you will find that and see that your coefficient a minus 1 will be equal to 0, right? And you should know the reason why will it happen, right? Okay, so therefore your answer will be I equal to 2 pi eta multiplied by sum of residues. Residues calculated at pi by 2, residue calculated at minus pi by 2, and residue calculated at 0, right? So the answer will be if you add these two, the answer will be 0, I think 0, right? This is the answer. So just keep in mind the fact that do not declare that all of these values are poles, right? Okay. Then taking another example. Example number 4. I equal to C dz over z to the power 6 plus 1, and this C is, I should take this C is a circle y is equal to under root 4 minus x square, and y is positive, right? Or should I write x equal to y equal to 0, comma y equal to 0, right? So this is a semicircle, the upper circle, right? Y is equal to under root of 4 minus x square, that is a circle, right? But and here we have plus sign also, and y equal to 0 means semicircle together with the diameter, right? In order to get the contour closed, I have to put this y equal to 0. You cannot just take this y is equal to under root of 4 minus x square. This is a semicircle in the upper half plane, but you should close your C, and in order to get a closed contour, you should take the diameter also. That's why we have added y equal to 0 here, right? Okay, solution. In order to find the singularities, you should put your denominator equal to 0, right? So put the denominator equal to 0, and you will get z to the power 6 equal to minus 1, right? And since this minus 1 can be written as cos 2n plus 1 pi plus eta sine 2n plus 1 pi, right? Where n is an integer, right? Since cos at odd pi is minus 1 and sine at odd pi is always 0, right? And in that way you will write this as e to the power eta 2n plus 1 pi, where n is an integer, right? And why don't we take this 6 here by 6, right? and n is any integer. But since it is an equation, it is a polynomial of degree 6, so it cannot have more than 6 roots, right? Okay. So I will write the 6 roots, the first 6 roots, and so I will start with 0, n equal to 0, 1, 2, 3, 4, 5. So these are 6 in numbers, right? So we restrict ourselves to write only 6 roots because this is a 6-degree equation, right? Okay. So I erase this. Okay. Now just plug 0. That will give you, that is, the first one will be, if you plug 0, that will be e to the power iota pi by 6. And the second one will be e to the power iota. If you plug 1 here, that's 3 pi by 6. That will become pi by 2. And e to the power iota, put 2, that will be 5, I think, 5 pi by 6, right? And then e to the power iota, 7 pi by 6, yeah, 7 pi by 6, and then e to the power iota, 9 pi by 6, and I think that will be 3 pi by 2, 3 pi by 2, and the last one will be e to the power iota, 11 pi by 6. So we have 6 poles, and why they are poles? Because if you differentiate this denominator, you will have 6 times z to the power 5, right? And then you plug any of these values, right, in 6 z to the power 5, you will get a non-zero number. That's why we are calling them simple poles, right? But not all of them will lie inside your semicircle. I will first draw the semicircle. Are simple poles, right? And why I am calling simple poles, you should know the reason, right? Now your semicircle, and this is obviously of radius 2, because if you square it, you will get y square equal to 4 minus x square, or x square plus y square equal to 4. So radius will be 2, right? This is your semicircle, and you just don't need a semicircle, you need a closed figure, and that is closed by this x-axis, y equal to 0, right? So this is a picture, semicircle together with the diameter, right? And now I will plot these poles. E to the power iota pi by 6. You focus on this angle. This is 30 degree, so it will lie somewhere here. And this circle is of radius 4. So if this is, sorry, radius 2. If this is 2, so here we will have 1 in the midway of these, right? So pi by 6 will be lying inside. Pi by 6 means 30 degree here. This is e to the power iota pi by 6. E to the power iota pi by 6, this point, right? Why I have plotted this point here? The first thing is that the angle is 30 degree. That is pretty clear that this angle is almost 30 degree, right? And if you take modulus of this complex number, you will get 1, right? E to the power iota theta have modulus always equal to 1. It means that its distance from the center will be 1. And since this distance is 2, so 1 will be almost here, right? Similarly, the another point will pi by 2 means 90 degree angle. The value will be here, e to the power iota pi by 2, right? And another is 5 pi by 6. It means that pi minus pi by 6 means 30 less than 180, 150, something like here, 150. E to the power iota 5 pi by 6. And what about these values? 7 pi by 6, it will lie outside, 7 pi by 6. And then e to the power iota 3 pi by 2, it will lie here, e to the power iota 3 pi by 2, sorry, 3 pi by 2, and the last is e to the power 11 iota 11 pi by 6. So you can see that all of these poles lie on the boundary of a unit circle. However, you can see that this is a unit circle, right? And all of them are lying on the boundary of that unit circle, right? But you are interested in those poles which lie inside your contour C, and only 3 of them are qualifying, right, which are lying inside the contour C, right? You have to ignore these 3. So I will find residue at these 3 poles only, not for these, according to my residue theorem, right? Only e to the power iota pi by 6, e to the power iota pi by 2, and e to the power eta 5 pi by 6 lie inside C. So we'll be evaluating the residues only at these points, right? Okay, so residue of fz at z equal to e to the power eta pi by 6 equal to, and since all of them are simple poles, so I will use that shortcut formula. The numerator is, where is the numerator? Numerator is 1, okay, and I will differentiate the denominator, that is 6z to the power 5, and then I will plug my z equal to e to the power eta pi by 6, right? And if you plug here it, you will get e to the power eta 5 pi by 6 in the denominator, and then it will be taken in the numerator. You will write it as 1 by 6 e to the power minus eta pi by 6, right? And then you can evaluate, it will become cos pi by 6 minus eta sin pi by 6. So cos pi by 6 means cos 30 is equal to root 3 by 2, and minus eta sin 30, that is 1 by 2. Okay, so this is the value of residue at this pole, right? Similarly, for other one, residue of fz at z equal to second pole. What is the second pole? E to the power eta pi by 2. Since the formula is same, so we'll have 1 over 6z. Okay, fine. Here we'll have 1 over 6 e to the power minus eta pi by 2, and cos 90 minus eta sin 90. So we'll get minus eta by 6, right? And residue of fz at third pole, what is that? Eta 5 pi by 6, we will have 1 by 6 e to the power minus eta 5 pi by 6. So it will become cos 5 pi by 6, that is cos pi minus pi by 6, that should be negative. So negative of root 3 by 2, and minus, it will become, okay, minus eta 1 by 2, right? And just use the formulas for cos and sin to evaluate cos of 5 pi by 6. Cos 5 pi by 6 is equal to cos pi minus pi by 6, and that will become minus of cos pi by 6, because cos pi minus theta is minus cos theta, right? And similarly for sin pi by 6 is equal to sin pi minus pi by 6, that will become sin pi by 6, because sin pi minus theta is sin theta. You have to remember all of those trigonometric identities, right? Now I will add them. Therefore my final answer would be 2 pi eta multiplied by their sum of these residues. If you sum them, I think this root 3 by 2 will be cancelled, and this will be added up. This will give you minus eta, I think, and 1 by 6 should be taken outside. Okay, it will give you minus eta, and from here you will obtain minus eta, right? And you will have minus 2 eta, right? And 4 pi, right? Eta square will become minus 1. 4 by 6, 2 by 3, 2 by 3, right? So this is your answer, right? Okay, take another example. Example number 4, not 4, 5. Example number 5. I equal to integral c e to the power 1 over z minus 2 dz, right? So this time I have taken an exponential function, and c is mod of z minus 1 equal to 3, right? Okay, so you can see that this function is not a rational function, obviously, and this function is not a quotient function, right? So you have to again rely on the original thing, that is Laurent series, right? You have to expand it, and you can see that z equal to 2 is the singularity of this function. If you plug z equal to 2 here, you will get e to the power infinity, right? So z equal to 2 is the singularity, essential singularity of this function, and that z equal to 2 will lie inside this C. We will draw the picture first. Solution. If you don't want to draw the picture every time, you just put that z equal to 2 here. You will get 2 minus 1, that is 1, right? Means the distance between your singularity and center is 1, but the radius is 3. It means that it will lie inside your circle, right? So clearly z equal to 2 is an essential singularity, right? And you should know the reason why we are writing it as essential singularity, right? Essential singularity is when you expand the function and you get infinite negative powers of z minus z naught, right? And if you allow yourself to expand this, you will see that there will be infinite negative powers of z minus 2, right? That's why it is an essential singularity. And lying inside your circle C, right? Okay. So just relying on the expansion, so writing expansion of e to the power z minus 2 equal to the first term will be 1 plus 1 over z minus 2 and then plus 1 over z minus 2 whole square by 2 factorial and so on, right? Therefore, the residue of fz, this is fz, at z equal to 2 will be equal to the coefficient of 1 over z minus 2, that is called a minus 1, and that is actually equal to 1 here, right? Therefore, the value of the integral is 2 pi eta times the sum of residues, and since there is only one residue, the answer will be 2 pi eta, right? Okay. Now I will take another example and yeah, something new. In all of these examples, we have seen that the singularity is lying within C or inside C, right? But what happens when a singularity lies on the boundary of the circle, boundary of the contour, right? The question is, in that case, does our Cauchy's residue theorem holds? Yes or no? The answer is positive. The Cauchy's residue theorem holds. Even the singularity is lying on the boundary of the contour, right? But the formula is modified, or you should say a more general formula, which occurs the case when the singularity is at the boundary of the contour also, right? So first I will rewrite that formula, a more general version of formula, Cauchy's residue theorem, general version of Cauchy's residue theorem, right? I will add the statement only, not the whole statement. And the formula says that the line integration of fz dz is equal to 2 pi eta times the sum of residues fz comma z equal to z I should write it I, right? And I equal to 1 to anything, right? I am not writing the range here, plus pi eta times summation of residues fz comma z equal to z boundary, so I will write B, okay, where zi are singularities inside C, right? This is the same part and this is the new part, and ZB are singularities on C, right? So for the singularities lying on the boundary of contour, we have this factor pi eta times this, right? And why only pi eta? The reason is that again that deformation principle, right? What do? You just replace that outer contour by small circles, right? And if the singularity is lying within the curve C, then there will be a full circle. But if a singularity is lying on the boundary of a C, you cannot draw a full circle there. There should be a semicircle of this nature. Suppose you have boundary here. This is your singularity, right? And then deformation theorem says that this C is replaced by a small circle, right? C1, just enclosing one singularity which is lying inside this C. But what happens at this point? You cannot draw full circle. You have to draw semicircle like this one, right? In that case, see this boundary, this one is just lying within your C, right? That's why this pi eta factor here. You cannot write 2 pi eta because here you will have a semicircle, right? In order to avoid this singularity, you have to draw semicircle, right? A full circle is not allowed, because in that case the full circle will go outside C, and you cannot use that theorem, right? So this accounts for this factor 1 here, right? Okay, so I will take example in which a singularity will lie on the boundary of contour, right? Example number 6, right? Evaluate I equal to dz over z minus 1, and the circle is mod z equal to 1, right? So this is the simplest example. You can see that z equal to 0 and z equal to 1 are simple poles, right? And z equal to 0 is lying inside the circle, but z equal to 1 lying on the boundary of the circle, right? So I will be able to use this modified version of this formula. Solution, rather I should write it directly, clearly. Z equal to 0 and z equal to 1 are simple poles, right? And this is lying inside C and this is lying on C. So therefore, I equal to 2 pi iota residue at z equal to 0, and for the pole lying on the boundary, we will multiply by pi iota residue of fz at z equal to 1, right? And the evaluation of this residue is similar. If I evaluate your residue at z equal to 0, you will multiply this by z, or you can again use that derivative formula, because these are simple poles, right? So derivative formula still holds here. Just write the numerator as it is and differentiate the denominator, and I think that will be z square, so it will be 2z minus 1, and then you will put z equal to 0, right? And for this case, pi iota, just write the numerator and differentiate the denominator, is 2z minus 1, and then z equal to 1, right? So you can use that formula here also, and I think this will be minus 2 pi iota, right? And this will be pi iota. The answer will be minus pi iota, right? Okay, taking another example in which this numerator part is also giving a singularity. So far in these questions, we have seen that the denominator part is giving the singularity. Sometimes there is a function f z such that the numerator part also gives a singularity. Suppose you have e to the power 1 by z in the numerator and z equal to 0 is a singularity, right? Then what will be your procedure? Okay, taking example of that nature, example number 7, evaluate I equal to integral e to the power 1 by z, and what if I take 0 will begin by this, so I have to take mod z, okay, and z, I think z is sufficient, or no, z minus 1, z square minus 1, that's fine, and I will take mod z equal to 2, right? Okay, dz, and you can see that your circle is centered at 0, radius equal to 2, and the singularity is given by the denominator are plus minus 1, and both of them are lying inside this circle. That is fine. Okay, but what happens here? See the numerator. If you plug z equal to 0 here, you will get infinity, right? It means that 0 is a singularity of this function, which is not given by the denominator, right? So do not get confused at this point. The singularities are not only given by the denominator, it may be due to the numerator function also, right? Such kind of function may give a singularity, right? So I will first I will find the singularity from the denominator plus minus 1, and then evaluate residue, then I will go to this numerator part, right? Solution, the singularities are z equal to plus minus 1 that are obtained from denominator, right? And both of them are simple poles, as well as and z equal to 0. You can see that z equal to 0 is a singularity given by the numerator, and do not write that they are it is simple pole. No, if you expand this, you will get infinite negative powers of z, and obviously that will be an essential singularity, right? Essential singularity. right? So first evaluating my residue at these points. Therefore, residue of function evaluated at 1, okay, and I think we'll use that formula z minus 1 multiplied by fz, right? And if you multiply this by z minus 1 will be cancelled up. You will be left with e to the power 1 by z over z plus 1, and I think answer will be e to the power 1 over 2, if I'm not wrong. Yes. And the residue fz at z equal to minus 1 equal to limit z tends to minus 1, z plus 1 this time multiplied by fz equal to, in that case z plus 1 will be cancelled and you will plug minus 1 e to the power minus 1 over, and the denominator will be having z minus 1, so that will become minus 2. Okay, right? Now the remaining singularity is z equal to 0, and for that I have to expand it, right? Now residue of fz at z equal to 0 is obtained by expanding my function, and that's 1 over z square minus 1 e to the power 1 over z, right? Obtained by expanding this function in powers of z only, because you are focusing on your singularity that is z equal to 0, so you should have an expansion in powers of z, right? So I will expand it, and I shall have to take minus common from here, 1 minus z square, right? Okay, and e to the power 1 by z. Now I can use that expansion, I think minus 1, and this will be okay, e to the power 1 by z. Now expanding, I have two expansions. First is this 1 minus alpha to the power minus 1, right? And that becomes 1 plus alpha square plus so on. All terms will be positive. And for this, we will have 1 plus 1 by z plus 1 by z square over 2 factorial and 1 by z cube over 3 factorial and so on, right? And now comes the important point. Since I need a residue, and in order to get a residue I need the coefficient of 1 by z only, so I will pick the coefficient of 1 by z rather than multiplying these series, right? So coefficient of 1 over z, and if you focus it closely you will see that when you multiply your 1 by this, then you will get 1 by z, right? And if you multiply your second term z square with this one, I think z cube, this one, you will get 1 by z, and then this term z to the power 4 by 1 by z to the power 5 over 5 factorial, right? You can see that this term is not required, this is not required, means all odd power, even powers of 1 by z are not required, and we need alternate terms in order to get the coefficient of 1 by z. Watch it very closely. If I multiply this 1 by z, then I will get, minus is still there, so I will get 1, and if I multiply this z square by this term, I will get 1 by 3 factorial, I think, plus 1 by 3 factorial, and then 1 by 5 factorial and so on, right? And this is actually, since all are odd factorial, so it will be sine hyperbolic 1, I think, sine hyperbolic 1, yes, okay, it will be minus of sine hyperbolic 1, right? If you remember the series of sine hyperbolic x, that is x plus x cube by 3 factorial, x plus x cube by 3 factorial plus x to the power 5 by 5 factorial and so on, odd powers of x, and then 3 factorial, 5 factorial, 7 factorial and so on, right? And in place of x we have 1, so this is an expansion for sine hyperbolic 1, right? And now I can evaluate my integral capital I equal to 2 pi eta and sum of these residues e by 2 minus e to the power minus 1 by 2 minus sine hyperbolic 1, right? And if you watch it closely, these two terms, they are just sine hyperbolic 1, right? You can write it as, take the 2 in the denominator like this, 2, and you will see that this is indeed the formula for sine hyperbolic 1, right? And then both will cancel each other, you will get 0, right? Taking another example, which must use that concept of winding number. So far we have been doing examples in which the winding number is considered as 1, right? So let us take my last example. Example number 8. Okay, let C be a positively oriented simple closed curve. I shouldn't write it simple, that closed curve, right? Orientated closed curve, not passing through eta, right? Okay. Find the set of values taken by the integral I equal to 1 over 2 pi eta, and here I will have C, and in the denominator I will write z square plus 1, and here I have write 2 eta dz, right? So you have C, positively oriented closed curve, and this time the simple word is excluded, and the curve is not passing through eta. The condition is that it should not pass through eta, and one more condition, it should lie in the upper half plane. See, the positive oriented closed curve not passing through eta in the upper half plane. Where should I write that? Where C lies in upper half plane, right? So you have to evaluate this integral, and you have to construct the set of values which is taken by this integral, right? Okay. Solution. Since the curve should not pass through eta, so there are two cases. Either the curve encloses eta, right, or the curve, the eta lies outside the curve, right? So taking two possibilities, case 1, when eta lies outside the curve, the picture will be like this. This is the y-axis, this is the x-axis, and this is the eta, right? Eta. And you assume that since the curve does not pass through eta, so there are two possibilities. One is this: the curve is not passing through eta, and the eta lies outside the curve, and the orientation is taken as positive. By positive we means anti-clockwise, right? So in that case, then I equal to 1 over 2 pi eta C 2 eta z square plus 1, and see this z square plus 1, z square plus 1 give you the singularities z equal to plus minus eta, obviously, right? Z equal to plus minus eta, right? And plus eta is, well, it is outside C, and minus eta will be obviously outside C, because the curve is not in the lower half plane. See this line, C lies in the upper half plane, so there is no possibility that its poles will lie inside C, because eta is outside C. You have assumed that, right? I will write it here. If eta lies outside C, right, and minus eta will clearly lie outside C, because C is in the upper half plane. So the answer of this integral will be 0. Since there are no singularities belonging to the inside of the curve C, so the answer will be 0. This result is obvious from that Cauchy's theorem. If some function is analytic inside some closed curve C, and there are no singularities inside it, then the answer is 0. Cauchy's theorem, right? I should write it here by Cauchy's theorem, right? And now I will come to the second case when the iota will belong to this inside of C, right? Case 2, and case 2 is when this iota is here and your curve is like this, enclosing this iota, right? And obviously this minus iota will again lie here, right? So in this case, z equal to iota is a simple pole of your function. Your function is fz equal to 2 iota over, what is that? Z square plus 1. I should take this also, right? Whole function 1 over 2 pi iota, 2 iota over z square plus 1, right? This is your function. Take this constant inside. So it's a simple pole lying inside C, lying inside C, right? So I will be evaluating the residue at this point and then multiply by 2 pi iota. Therefore, residue of your function at iota will be given by, since it is a simple pole, you can use the differentiation rule also. Write the numerator as it is and differentiate the denominator. You will get 2z, I think that will become 4 pi iota z, right? And then you plug your z equal to iota here, right? And plug z equal to iota, you will get, I think, yeah, this will be cancelled, 2 iota, and you will get 1 over 2 pi iota, right? And you can rationalize it, I think, on rationalization, or you just leave it, right? So this is your residue, and now you will use your residue theorem, a general version of residue theorem where you don't know about the winding number, right? In this example, I am assuming that the curve can take infinitely many orientations or infinitely many loops, right? So there will be n, omega, winding number is omega, right? It can wind around iota infinite number of times because the curve is not simple, right? So you should consider the case when this C is like this one. See this. You start from here, okay? You go like this, okay, and this way, right? This is also possible because the curve is not simple. A simple curve is that which does not intersect itself, right? But since it is not simple, so the curve may intersect itself. So the possibility is like this one, right? And you can see that your curve is winding around your pole twice. This is the first time, and this is the second time it's winding around your pole iota. So you are taking two integrals actually, right? So the answer should be multiplied by 2, right? Or if you take 3 orientations, 3 times 3 winding number, then you should multiply it by 3. It means I will multiply my answer with omega. Omega starts from 1, 2, 3, and so on. You can minimally you can take 1 winding number, 2 winding number, 3, and so on. I will write that here. Therefore, I equal to 2 pi iota omega multiplied by residue, and your residue is 1 over 2 pi iota, and you will be left with omega. And you know that omega is a winding number, and that starts from 1, 2, 3, and so on, right? A non-negative, or you should say an integer, a natural number, right, is winding number of curve C, right? So I have to construct the set of values taken by I. I can take value 0 if this curve does not enclose this pole, and if this curve encloses this pole in so many ways, just 1 winding number, 2 winding number, 3, and so on, the answer will be omega. So the set of values is, therefore, the required set will be 0 from here, and omega starts from 1, 2, 3, and so on, right? So this is the required set, or you can write it as z plus non-negative integers, right? Just leave that, non-negative integers, right? Okay, so we have seen the application of Cauchy's residue theorem in its 2 or 3 versions, right? And this is it for this video. In the next video, we will be seeing application of residue in evaluating some general integral that will involve a real integral. So far, we have been evaluating the complex integral. This residue theory can also be used to evaluate a real integral, the integral over a real line, integral of fx dx, right? And that should be definite integral. That will be part of our next video. For this video, thanks.